Hey, folks. So I'm going to walk you through the basics of weathering. Okay, there's another part of this second video that's going to be on soils, and in that video, we're talking about things that we didn't actually do this year because I'm recycling it from actually 2020. So, but it does a job of going over soils. Okay, so we're doing different. We do different projects with soils every year, and there have been times where we've done tombstone surveys, septic surveys, and other things. So a lot of what you're going to see here is based on septic stuff. I'm going to go kind of through it kind of quickly because I did mention it today that one of the reasons you would be interested in soil texture and soil infiltration rates would be septic systems and drain fields. And so, not that this little kid here is going to be playing in a septic system. If that's a drain field in the yard, that's bad news. But hopefully, most of you have had an experience like this young individual has had right here, right? So, all right, moving on here. So, let's see if I can figure out how to work. I don't usually work these controls. So, um, okay. All right, we'll try this here. So, this was a public service announcement put together by the United Nations, um, UNICEF specifically, about open defecation, actually in the Indian subcontinent, where I mean, this is still where people this is still a way people relieve themselves all over the world, not just there. When you're out camping, you might do this sort of thing, right? So anyway, this goes on about like the issues with that in terms of uh, you know public health and all of that. So, all right, moving on again, septic systems, yada yada yada, perk tests, infiltration tests. Um, Hopefully that's you know somebody's got to do it, right? So um, we're going to move on to talk about, well, briefly, Stokes' law. Stokes' law deals with settling rates, and so one of the ways we can talk about sand, silt, and clay fractions is one of the tests we can do for that is settling in a large graduated cylinder, and of course, as we do that, and you pour the sediment in, you shake it up. What's going to settle out first is going to be your larger particles, followed by the next smallest, next smallest, next smallest, and that's all based on something called Stokes' law. And we'll do a lab on this here. It'll be mostly on your own. We're not going to actually deal with it in class, at least not very much. It'll be a spreadsheet lab, so it's mostly math actually. Uh, Stokes' the scientific laws are mathematical formulae, so that's what we're dealing with here. And Stokes' law does a good job of dealing with particle settling within a particular range of particles and range of conditions, and beyond which it gives you a model to work with, but doesn't necessarily work all that well. So within the parameters, certain parameters, it works well. Okay, so weathering are collections of processes that are either physically or chemically break down materials, rocks in particular. So they can be wave action, wind action. Those are erosion. Those winds and waves, I should say. Erosion are transport processes. So weathering processes break things down in situ. Erosional processes carry things away, and so um, there are a variety of mechanical weathering processes. I'm not going to belabor this. You can pause here and take a look at them. And they all occur basically because you have a highland someplace that's getting worn down, and those materials then erode or get carried down into a basin of water somewhere, into a basin where they collect and become layers of sediment, like we looked at last semester. The sedimentary layers, and that records a history of things, right? So we're all familiar with that. That's stuff we've dealt with. It's the weathering processes themselves, the nitty gritty, right? So this is one of these the biogeochemical processes that have been mentioned so far this semester. This is a part of where some of these materials cycle through these biogeochemical processes are through weathering. And so we talked about sand, silts, and clays. And when you're transporting sand, silts, and clays, there are certain grain sizes that behave a certain way under certain velocity regimes. And so this is, lower velocity or low energy regimes, and higher velocity or higher energy regimes. And of course, to move a large cobble or boulder, this is grain size down over here, it's very easy to move clay, but even at a certain velocity, at certain slow velocities, clay doesn't even necessarily get picked up off of the bed and moved. So sedimentation of particles onto the bed is this sort of tan area, and that's where stuff's being carried along on the bed of a stream. And then there's a transition zone, and then where stuff is picked up and carried up in the water column. That's what's going on up here. So to pick up a boulder or a cobble in the water column, you got to have some really moving water, right? So it's really got to be moving. We're going to skip. Oh, these are some examples of some of the weathering processes. This is mostly frost wedging and um, warming and cooling of rock and then breaking down from. Then of course spheroidal weathering, and this is some, of course, physical weathering from wind, abrasion, and root wedging, and so forth. Chemical weathering is the one you're probably less familiar with because there are three major processes involved here. One is dissolution. That's what we get with karst. We've been talking about the results of dissolution weathering, so you're familiar with those actually. But it's hydrolysis and oxidation that I want to spend most of my time on here. And so it's worth noting that seawater has salts in it that come from weathered materials off of land. The oceans are salty because of weathering. So that is one of our big questions for the semester: is why are the oceans salty, right? So the water is fresh water, has no mineral content in it. Distilled water is pure H2O. But here we're looking at a situation where we have 35 parts per thousand salt in a typical ocean water, and we have to ask ourselves, where does that come from? Well, these are the components of salt water, primarily these, and then there's a whole lot of other things, including gold. Gold's in there as well. But yeah, you can mine gold from salt water, from seawater rather. But most of it is chlorine and sodium, followed by some other minerals, right? So this is another way. This is a really awkward graph, the way it's depicted here. But this is looking at salinity of the water in parts per thousand, and the types of environments. Freshwater is all the way down here between 0.5 and 0, PPT, and then brackish water is somewhat salty, and then of course ocean water, and then briny water up here. So, all right. So some materials do precipitate from water as well. So when you evaporate water away, this isn't weathering and erosion. I'm just throwing this in here because these are evaporite deposits. The salts are left behind. And when salts are left behind, the first salt that gets left behind is actually the calcite, calcium carbonate, followed by gypsum, calcium sulfate, followed by halite, which is what you usually think of when you think of salt water. That's actually the third thing to preferentially dissolve. This is why we have such huge layers of limestone in various places, including the valley. And then gypsum is really common. In fact, the walls in your house are probably made from gypsum. That's drywall, and so forth. But sea salts, when you have sea salt contains more than one of these, right? So your typical, Epsom salt is a sulfite or a magnesium sulfate. It's up here, but table salt is typically sodium chloride. But when you're using sea salts, you're getting all of those. So that's why sea salt does tend to be more mineral rich. When you're dissolving, you're actually pulling ions away from the structure. And an example of dissolution, this is the opposite of an evaporite deposit when you're precipitating materials. In carbonation, which is what we got going on in cave environments, you're taking carbon dioxide plus water, which creates a weak carbonic acid, and you're going to combine that with, there's the carbonic acid, combine that with calcium carbonate, and you end up with calcium bicarbonate in solution. And that leads to the dissolution of limestone. And then, of course, as the water gets into an open cavern, it reprecipitates calcium carbonate in the form of speleothems through dripping water and so forth. We've already been through all of that. And this is the part that I really want to go back to. And I will say that on the mid-year assessment, Bowen's reaction series was a bit of a rough question. So Bowen's reaction series is one of the ways we talk about one of the things we start with when we start talking about igneous rocks, particularly with volcanism and so forth. But as you cool a magma from really, really hot and molten down to less hot and starting to become kind of solid, you crystallize out different minerals, and they either move down along this series, the discontinuous series, or they move down along the feldspar series or the continuous series. All that's going on here is you have a particular crystal structure, and certain ions get subbed in: calcium, sodium, potassium. Here you get completely different minerals. So you start off with iron and magnesium. Those all get incorporated. By the time you're done crystallizing olivine, the iron and magnesium is largely gone, and then you're crystallizing pyroxene and amphiboles, biotite micas, and eventually you get down here to the granitic or felsic rocks, and you're precipitating stuff that makes up granite: potassium, the pink feldspar, muscovite mica, and quartz. This is what you typically find in granites. It just so happens that weathering processes are also described this way. So over here we have processes that are, let's start over here. Processes dominated by hydrolysis. I'm going to give up on this really quickly here. I thought I would try to do this way. All right, that's hydrolysis, and over here, you said it, oxidation, right? So this is oxidation. This is where we're adding oxygens, and we're going to break these things down. These are basically going to rust, not really necessarily produce rust, but they're going to convert from one mineral to another through oxidation processes there. And these are going to convert from one mineral to another through hydrolysis. Hydrolysis is one of the ways that ocean carbonates carbonates get put into the ocean. Bicarbonate is sourced through hydrolysis. Hydrolysis is important for that. So if we move on here, we're going to go to the next thing here. So as we move along here, you got these minerals here. So the fastest weathering occurs along with the slowest weathering with the most stable minerals, the fastest weathering with the least stable minerals. And so you can see where these minerals fall. Typically, these minerals over here are the least stable up here, and these are the most stable down here. So you're going to break down through oxidation this side pretty quickly, and this side pretty quickly through hydrolysis. And when you do that, you're releasing ions, and they become clay minerals eventually. And then these are the ones that are really tough to break down. So oxidation, of course, is where you're adding. It's when ferrous iron is oxidized by oxygen, or magnesium is oxidized by oxygen, and combining with water and then precipitating a solid, or iron oxide or magnesium oxide from a solution. Hydrolysis is where you're taking the feldspar mineral of whatever it is. This happens to be calcium feldspar, combining it with carbonic acid from the atmosphere again, which then produces a kaolinite, and then of course ions that are precipitated in solution. So, or that are dissolved in solution. So they're aqueous at this point. So feldspar is converted to the clay mineral kaolinite, calcium feldspar, through this process, and it's basically the same stuff that's dissolving limestone, just now you're dissolving feldspars, and this takes a lot longer. It's not real quick. But what we can do is we can look at the climate of an area and predict what kinds of clay minerals we're preferentially going to get as a product of these weathering phenomena. So in an arid climate, if you hydrolyze potassium feldspar and olivine, you're going to end up with a smectite clay. It's a special kind of clay called a smectite. Notice here at the beginning of these equations, it's always the same: feldspar, olivine, carbonic acid, feldspar, olivine, carbonic acid, water in this case, because now you have a moderate climate, a moderately wet climate. Here you have a very wet climate. You're adding a lot more water. It says 14 H2Os here, 9 H2Os here. But again, feldspar, olivine, carbonic acid. So you're not adding much in the way of water, if anything. Here you're adding some water, and here you're adding a lot of water. And you end up with dissolved ions, dissolved ions, dissolved ions, bicarbonate plus silica, silicic acid in both these cases. No dissolved silica up here. And so dissolved silica concentrations can tell you something about the climate. That's worth noting. We can actually test for dissolved silica in the lab with the spectrophotometry. But you'll end up with smectite, kaolinite, or gibbsite, or a variety of other clay minerals through these processes as you break these things down. So if we go back to Bowen's reaction series, we get oxidative weathering over here and hydrolysis weathering over here. And of course, this is what's called McClellan's weathering sequence. These are the more resistant minerals down here, and these are the less resistant to minerals up here, resistant to weathering minerals up here, and so forth. So you can pause it here and take a look at this image for a little while and study it. All right. Clay formation, there are really two main types of clays. One is residual. Most of what we're looking at is residual, and some are transported, like moved from one place to another. There are three groups of clay minerals: kaolinite, montmorillonite, illite. and they look different under a scanning electron microscope than one another. Kaolinite tends to stack up in these columns, like these things here that are stacked. This is the crystal structure of a kaolinite layer. Illite tends to kind of stack in flattish sheets or collections of mineral matter. And Montmorillonite looks more like the inside of a hornet's nest. This is a quartz grain over here, but you can see the Montmorillonite clay minerals over here. And so there are other forms of chemical weathering and that occur in conjunction with mechanical weathering. You can pause and take a look at these as well. There's some examples of these. That's exfoliation, by the way. Somebody's pulling skin off their face like that. I love that. It catches your attention, right? This is spheroidal weathering. This is what happens to granite in out there. Granite has both oxidation and hydrolysis working on it. So, all right, and then we get to soil. So I'm going to stop there and pick up where you left off there with soil.